Hello everyone, welcome to the postgraduate conference. This is Junde Zhang from USW CNE. Today, my topic is the CR structures on nilpotent Lie groups and flag manifolds. So, before really talking about the definition of CR structure, let's first have a look some important conceptions and definitions that we're going to use a lot in this talk. So the first terminology that I want to introduce is called the stratified Lie group, and this is connected and simply connected Lie group whose Lie algebra admits a stratification. So a stratification on a Lie algebra means that this Lie algebra has a decomposition in a vector space direct sum like this. So the first linear subspace N1 generalize all the linear subspaces by the Lie brackets. So for example, we got N2 equal to the Lie brackets of N1, N1, and N3 equal to the Lie brackets of N1, N2, and so on. Now, we count the first linear subspace N1 as the horizontal distribution, and we're going to use this notation a lot in this talk. Then, the main topics in this talk is actually about a real stratified Lie group that carries a complexified horizontal distribution, and we also want to talk about the map that preserve the complexified horizontal distribution. Because we really want a real linear subspace that can admit a complex structure, so the next terminology that I want to define is called a complex structure. So with this kind of structure, we can actually define a complex manifold in an algebraic way. So first, geometrically, a complex manifold can be defined as a topological space that locally equivalent to a neighborhood of Cn. So for example, we got Cn itself is a complex manifold, and complex projective space, a complex projective plane, or the Riemannian sphere. So before, so an algebraic way to define an almost complete structure requires a terminology which is called almost complete structure. Given an even dimensional real manifold, so for any point P, we can actually define a linear isomorphism on the tangent space of it. Uh, satisfy, satisfies the property that the square of this linear map equal to the minus identity. Also notice that this linear map is actually varies smoothly on entire tangent space. So we can actually extend this definition into a tensor field, so that this tensor field is still called almost complete structure, can be defined on a tangent bundle. So a real manifold, a even dimensional real manifold amidst this almost complete structure is so-called almost complex manifold, but this is not yet a complex manifold. For example, we got a six-dimensional sphere S6 is actually an even dimension is actually an almost complex manifold, but it's not a complex manifold. So we need to stay. So in order to make an almost complex manifold into a complex manifold, we have the following theory, and this theory state necessary and sufficient condition so that an almost complex structure in to be an integrable almost complex structure, that is a complex structure. So given an almost complex manifold, an almost complex structure is a complex structure if and only if the Nugent-Hauss tensor equal to 0. So by a Nugent-Hauss tensor, we mean a type 1-2 tensor formulated by the Lie brackets and the almost complete structure defined on the section of tangent bundle like this. And we're going to use this Nugent-Hauss tensor a lot to define the CR structure and CR mapping, and in some examples we're going to talk about later. So with those terminologies, we can actually define the CR structure and CR manifold. Uh, First, let M be a real M-dimensional smooth manifold, and T01M is a complex subbundle with complex rank N, and this T01M is a CR manifold must satisfy the following conditions. The first one is the intersection of this complex subbundle with its complex conjugation is actually zero element, and the second condition is actually this complex subbundle is integrable. So any real manifold that made a CR structure is actually called a CR manifold. Generally, we call a pair M and the CR structure is an abstract CR manifold of type Nk, and here this N is a complex rank of the CR structure, and we also call this N as a CR dimension, and this K here is actually a CR codimension. It's actually a CR codimension, and this K is given by the total dimension of this real manifold M minus the real dimension of the CR structure. And in particularly, if this real manifold M is actually the submanifold of a complex Euclidean space, and the CR structure is actually and the CR structure is particularly defined as a holomorphic tangent vector space of Cn intersect with the compactification of the tangent bundle. So in this pair we call this pair as an embedded CR manifold of type Nk. And there's a interesting questions in CR geometry that is to find a CR equivalence between abstract CR manifold and an embedded CR manifold. And we're going to introduce an example later. So we now have a look how those definition works on a real stratified Lie group. So we take M equal to N and M10 as a complex subalgebra so that this complex subalgebra intersect with its complex conjugation is equal to zero element. And so this condition is actually satisfies the first conditions of to be a CR structure. Then we're going to have a look at the second one. So take N1 as a horizontal distribution. This N1 equal to the real part of the direct sum of M10 and its complex conjugation, and define an almost complex structure on this horizontal distribution. And what we want is really this almost complex structure becoming an integrable. That is, by the Newlander theory, the condition to satisfy this almost complex structure to be a complex structure is that the Newton-Haus tensor is vanished. So we have this condition. And if this condition is satisfied, we are going to we just say the complex subalgebra M10 is a CR structure, and any real stratified Lie group admits this CR structure is called a CR stratified Lie group. So with this definition, we're going to see some example and see how those definitions works on those examples. The first one is called Heisenberg group. We can actually relate this group as the old dimensional Euclidean space, and with the coordinates zt, where z belongs to the Cn and t is just a real number. And we choose the holomorphic tangent vector field Tj equal to the half of xj minus iyj, where this xj and yj actually spans the horizontal distribution. And by this choice of Tj, by this choice of holomorphic tangent vector field, we can just say because this Tj is definitely not equal to its complex conjugate, so the first condition is automatically satisfied. And the second one, because we want to prove the horizontal distribution can be complexified, so we define an almost complex structure that mapping from xj to yj and yj to minus xj. And also notice that the Lie brackets of those vector fields has the relation that the Lie precase of xj yj is actually equal to only one element t. So with those conditions, with those two conditions, we can actually say that we can actually say that the Nugent-Hauss tensor on the horizontal distribution is actually zero, and hence the almost complete structure is exactly complete structure, and the horizontal distribution can be complexified, and the Heisenberg group is indeed a abstract CR manifold of type n1 because we only have one element t as our codimension in our codimension, actually in our second line, and we usually call a CR manifold with CR codimension 1 as CR hypersurface. So in another word, the Heisenberg group is also called as abstract CR hypersurface. So also there's another example. There's a different example for the CR hypersurface. For example, the odd-dimensional sphere S2 and plus 1, and for the corresponding embedded CR manifold, we have the boundary of Siegel domain defined like this, and you can see that this is a submanifold of Cn plus 1, and we're going to show later that there actually exists a CR equivalent among those three CR hypersurfaces. So by CR equivalent, that means mapping from one CR manifold to another CR manifold. The first thing is this mapping is diffeomorphism, and second thing is this mapping preserves the horizontal distribution and also commute with the complete structure that corresponding to each horizontal distribution of the CR manifold. And of course, those two CR manifolds must have the same type. And now we can have a look at our next example, which is called the Andrew group. This is a real four-dimensional Lie group with step 3 stratification, which means the Lie algebra n has a decomposition n1, n2, n3, and n1 by left invariant vector field given by x1, x2, yz. We have n1. We have the horizontal distribution is actually given by the span of x1 and x2. And then we can choose the holomorphic tangent vector field equal to x1 minus I x2 over 2. And because the holomorphic tangent vector field in this case is not equal to its complete conjugation, so the first condition to be the CR structure is automatically satisfied. And now we're going to have a look at the second one. So we define almost complete structure on the horizontal distribution by x1 mapping to x2 and x2 mapping to minus x1. And we also know that the Lie relation for x1, x2 is actually given by the Lie of x1, x2 equal to y. And with those conditions, we have that the almost complete structure defined on HE horizontal distribution is actually a complete structure, and hence the Andrew group is actually a CR manifold of type 1, 2, because we got two elements on the codimension. So the corresponding embedded CR manifold is given by the cubic form. This is a submanifold of complex of C3, and actually it has a lot of further properties. So I don't want to introduce all of them in this talk, and let's move on to the next part, which is a CR equivalent on CR hypersurface. So because we already know at Heisenberg group the boundary of Siegel domain and odd-dimensional spheres are three CR hypersurface, and this theory actually states that we have the following CR equivalence. That is, this mapping phi and f are actually CR isomorphism. So because we already know the coordinate on the boundary of Siegel domain, and we also know the coordinate in the Heisenberg group, so this f can be easily to write down. and we can calculate the push forward of F so that this F is a diffeomorphism and preserve the horizontal distribution and so on. And another thing is to prove that this little phi is a CR isomorphism, and this part is not really easy. By doing so, we have to use the next lemma. We have to introduce Kähler transform, and this is a biholomorphic mapping that maps from a unit ball to the single domain, and by restricting to the boundary of a unit ball minus a point, we actually can have this little phi. So what we only need to do is calculate the push forward of this capital phi. So by simple calculation, you can verify that okay, this little phi here is actually a CR isomorphism. So in this way, we can prove the theory. So from this theory, we actually can have the following observations. The first observation is that the phi prime defined from S2n plus 1 minus a point Heisenberg group is actually a CR isomorphism. Because we know that the composition of two CR maps is still a CR map, and phi and F defined in the theory is actually CR isomorphisms. So the phi prime is indeed a CR isomorphism. That is, this means a CR structures on odd-dimensional sphere is actually preserved in a one-point compactification of the Heisenberg group. And this is the first observation. And another one is we can actually identify this odd-dimensional sphere as a homogeneous space, homogeneous space. And this homogeneous space is given by the special unitary group SUn plus 1 quotient by its Borel subgroup. So, and this types of homogeneous space is also called Fleck manifold. So, yeah, because the Heisenberg group is actually the nilpotent part of nilpotent subgroup of SUn plus 1. And in another word, we can have a mapping from a Heisenberg group to Fleck manifold via one-point compactification, so that the CR structure from Heisenberg group is also preserved in a real Fleck manifold J mod B. So from those two observations, we finally have the following questions. So the first one is we have the following sequence so that this F and phi are CR maps. So we first assume that this J is a real semi-simple V group and B is its Borel subgroup. So J quotient B gives a generalized Fleck manifold. And we assume that N is an Iwasawa nilpotent subgroup. By Iwasawa nilpotent subgroup, I mean that where the Iwasawa decomposition of J, N is a Iwasawa part in this Iwasawa decomposition. So we call this Iwasawa nilpotent subgroup. So this Iwasawa, we assume that this Iwasawa nilpotent subgroup admits a CR structure, and omega here is an embedded CR manifold with the same CR type of N, and we want to show that, and also by the Borheit decomposition, we know that this J mod B is actually can be decomposed in terms of the N orbits, and the nilpotent subgroup N is actually the open and dense subset of this J mod B. So in another word, this J mod B can be viewed as a compactification of N. So my question is, if N has a CR structure, can this compactification still preserve the CR structure from N to J mod B? So this is the first question. And for example, we have N equal to Andrew group, and we already know in example 2 that the omega is actually the cubic form, and we can actually find a CR isomorphism from omega from cubic form to Andrew group. And also Andrew group is actually the nilpotent part of real symplectic group sp2r, and sp2r quotient by its Borel subgroup is actually a Lagrange Fleck manifold. So my questions in this example is that can we prove that phi is a CR map so that this phi preserves the CR structure from N to J mod B? And finally, the last questions in this talk is given a real stratified V group N. So because we have already know the conditions that N admits a CR structure, so under what conditions there doesn't admit an integrable almost complete structure, which means a complete structure, so that N admits no CR structure. For example, if we're taking J equal to if we're taking a real semi-single V group SL5R, that is special linear group, and N is actually the nilpotent subgroup of SL5R, which admits a four-dimensional horizontal distribution because SL5R has actually four simple roots. And in this case, the second layer is actually only generated by three elements, and we cannot actually find an integrable almost complete structure. So that is all for my talk, and thank you for listening.